Assalamualaikum and very good day. I'm Dr. Hidayah from the School of Civil Engineering, Faculty of Engineering, University Technology Malaysia. First, I would like to welcome everyone to my lecture video. This video is for online learning for the course of Highway Engineering. In this video, I will discuss on Marshall Mix design. I hope this video will benefit you and others. Okay, you can refer to your notes on job mix formula. So basically, what we need to do in order to design the asphalt mixture. First, we need to design the aggregate gradation using aggregate blending because as we know that asphalt mixture contain various aggregate sizes from different stockpiles. Therefore, the aggregate needs to be blended and determined for the right portion as what we have discussed before. So this can be referred to exercise 2.9.2 and 2.9.3. Okay, next what we need to do is to determine the bitumen content, OBC, and why we need to consider as optimum. Because we don't want it to be too much. As too much bitumen will cause the problem of bleeding and reduce skid resistance. And if it's too little bitumen inside the asphalt mixture, then it will cause lack of bonding between aggregate and binder. And this also could lead to stripping and raveling problem. So both need to be designed and make sure comply with the specification. Okay, in this video, we will focus on Marshall Mix design, which refers to the method to determine the design or optimum bitumen content for the targeted asphalt mix. This is subjected to volumetric analysis and Marshall testing procedure. Before we go into details calculation, we need to know a few parameters involved in the calculation which are called volumetric properties. So what exactly is volumetric analysis? It can be referred to the process to determine the volume of aggregate and bitumen required to produce a mixture with desired properties. So what are the volumetric properties? From the slide, we have VTM, void in total mix, which refers to the void exists between aggregate. And then VMA, voids in mineral aggregate, which refers to the spaces between aggregate. And finally, VFB, voids filled with bitumen, which refers to the volume of bitumen that coat the aggregate particles. Okay, to simplify the explanation, you can refer to the illustration provided in the slide. As you can see here, we have the aggregate coated bitumen, VEAC, and then absorbed bitumen, VAAC, and finally the air voids, VV. The coated bitumen or asphalt binder termed as effective asphalt binder or effective bitumen. Why? Because it's effectively coat the aggregate particles and function as a binder. While for VAAC refers to the small portion of asphalt binder or bitumen that is absorbed on the surface of aggregate particles due to the surface roughness. So, looking at the formula of VTM, which is VV, volume of voids, divided by volume of total. And then for VMA, the formula is VV, volume of voids, plus with volume of effective asphalt content, VEAC, divided by volume of total, which refers to the spaces between aggregates. And then VFB refers to the formula VEAC divided by a total of VEAC plus volume of voids, which refers to the coated bitumen. So next, after we clear on the volumetric properties, then we can do the Marshall Mix design. So basically, what's the objective of Marshall Mix design? The Marshall Mix design is conducted to determine the optimum bitumen content in order to ensure the good performance and quality of the asphalt mixture. As you can see from the slide, these are the steps that need to be taken prior to and during the OBC determination. Steps 1 to 5 are taken prior to the determination, which involve first, aggregate and bitumen selection. For example, the granite aggregate and 60-70 penetration bitumen. Then, grading selection, which refers to the mix type, whether it's AC10, AC14 or AC28. And then, aggregate proportion, which is determined from the blending of aggregate from different stockpiles or sizes. And then determine specific gravity of blended aggregate, the SG of the coarse aggregate and SG of the fine aggregate. Finally, the step number 5 is to determine the mixing and compaction temperatures for the asphalt mixture preparation, which depends on bitumen grade. The harder the bitumen, the higher the temperature of the mixing and compaction. On the other hand, steps number 6 to 10 are conducted during the OBC determination. So first, we have to prepare the compacted sample at different trial bitumen content. As highlighted earlier, our target is to determine the optimum bitumen content. So we need to do a few trials with 3 to 4 samples for each trial bitumen content, with the increments of 0.5% bitumen content, using 75 blows Marshall compaction. Okay, to clarify this, what exactly the trial bitumen content and how the sample is compacted. Okay, let's have a look on the next slide. Okay, this is the standard specified for the design bitumen content for all the 3 mixtures as recommended by JKR specification. Okay, according to the table provided in this slide, AC10 and AC14 is used for wearing course and AC28 is used for binder course. So for example of AC14 for wearing course, the bitumen content is specified at 4% to 6%. Therefore, for the trial bitumen content, it is proposed at 4%, 4.5%, 5%, 5.5%, and 6%. Like what we have mentioned earlier, the selection for trial bitumen content is at increment of 0.5%. And the same goes for other mixture. So if you refer to the Marshall form, as in the exercise 2.9.4, the values are provided in column B. Okay, let's have a look on Marshall form. Okay, according to this Marshall form, the bitumen content can be found in column B. So as you can see here, we have the first trial of 4%, 4.5%, 5%, and then 5.5%, and finally 6% trial bitumen content. So here we can see the difference in increment is 0.5% as recommended by GKR specification. So after we have selected the value of the trial bitumen content, then we need to prepare the sample of loose mix. So the way we calculate the portion of aggregate and bitumen is, for example, we have 4% bitumen, meaning that the rest out of 100% is 96% of aggregate content. So how to calculate the total weight of each sample? So normally, for Marshall sample, the total weight of each sample is 1,200 gram or 1.2 kilos. So the percentage of bitumen content and aggregate content is calculated by taking the percentage of, let's say, for the first trial, 4% bitumen content and 96% aggregate content by the total weight of 1,200 gram. Okay, next, let's have a look on the compaction procedure. This slide shows the Marshall compactor and then the different combination of aggregate sizes. The Marshall mold in cylindrical shape, so that's why our sample will be in cylindrical shape with the size of 100 mm diameter and around 60 mm for the thickness. After mixing the asphalt and aggregate with different sizes, the loose samples as shown in the photo is then compacted for 75 blows per face. And then after finish, for the top surface of the sample, turn the sample upside down and then compact another 75 blows on the sample. Then, step number 7. After the compacted samples are ready, we need to determine the density of the sample. Let's have a look on the procedure. After the samples cool to the room temperature, which is normally left overnight, the samples are extruded from the mold and determined for density or specific gravity by measuring the weight of the samples in air, then soak in water and take the weight in water, and then remove from the water and dry with damp towel and take the weight of saturated surface dry or SSD. Then, as referred to the Marshall form, the data is filled in the column C, D, and E. And this data is used to calculate the density or specific gravity for the compacted sample as specified in column F and G. Okay, now let's refer to the Marshall form again. From the Marshall form, refer to column C, which is weight of SSD, and then column D is weight in air, and column E, weight in water. Each trial has 3 samples, then the bulk specific gravity for the compacted samples are calculated using the formula in column F and G. The values are then averaged as shown in column G. The same calculation applies for all the trial bitumen content sample. So based on the exercise provided, you can continue the calculation of bulk specific gravity for the other bitumen trial. Okay, let's continue with the next step. Step number 8, we have to conduct Marshall stability and flow test using the compacted samples. Okay, let's have a look on the procedure. As shown in the slide, before the stability test is conducted, the compacted samples are conditioned in the water bath for 30 to 40 minutes at the temperature of 60 degrees Celsius and then tested for stability and flow. The compression load is applied to the sample and the maximum load before failure is taken together with the flow or the reading of the deformation after the compression. All the compacted samples were tested for the Marshall stability. Then, the data is included in the Marshall form. Let's have a look on the Marshall form again. Okay, refer to column P is the value of stability in kilogram. Column Q is the value of stability after correction. How to do the correction? Later, we will go through the calculation. And column R is the flow value. Each trial has 3 samples. Then, the stiffness of the samples is calculated by taking the ratio of the stability and flow as shown in the column S. Then, after we have all the values determined from the density and Marshall stability, we now can go to step number 9 to complete the detailed calculation of the Marshall form and plot the test results for bulk density, stability, flow, VTM and VFB versus bitumen content. And then step number 10 is to determine the OBC and compare with the specification. This is to verify the value determined with the standard. Okay, this is an example of Marshall form. Bear with me as we will go through the form and calculation involved together. At the same time, you can refer to your exercise on Marshall form. First, it should be noted that the form consists of many columns which are labeled with alphabetical order A, B, C until S. Please have a look on each column. Every column has its parameter highlighted and some have formula for the detailed calculation of the parameters. Let's start with column A, where from the Marshall form, we can see no calculation or value involved because this column is just to highlight the average and later the calculation will be considered for the average value. Then we have column B. It's the trial bitumen content as highlighted earlier. Then column C, D, E, F, G also as mentioned earlier for the SG determination. Then the calculation is continued with column H. It's the theoretical maximum density which can be calculated by referring to this equation. Okay, let's try once for the calculation of column H. It's TMD. Based on the formula given, H is the value of the TMD, and then 100 divided by P aggregate. P aggregate is referred to the percentage of aggregate. In this case, the trial bitumen content is 4%. 100 minus 4% is equal to 96% of aggregate content. Then, SG effective in this case is 2.668. Then, plus B, which is referred to column B for the trial bitumen content. And then SG bitumen is referred in this case 1.03. The example of H calculation is provided in the slide. The same calculation applies to the rest of the trial bitumen content. And for example, the second trial of 4.5% bitumen content, the percentage of aggregate will be 100 minus 4.5% bitumen content, which is now 95.5%. Then, continue the calculation for column I and J. I is the volume of bitumen and J is the volume of aggregate in percentage. Okay, let's try to do the calculation for column I and J based on the data given in the Marshall form. You can use the formula given in the column. After that, continue the calculation for column K, L, M, and N. These are the volumetric properties that we have discussed earlier. K is the volume of voids. L is the volume of voids in mineral aggregate VMA, and M is the volume of voids filled with bitumen VFB. And finally, column N refers to the voids in total mix, which is VTM. Again, you can try to do the calculation using the formula given in the column. Next, let's have a look on column O, is the correction factor. So how to determine the correction factor? This correction factor later will be used to calculate the value of stability. To determine the correction factor, you can refer to the small table at the top of the Marshall form. In the small table, you can see the volume and also the value of the correction factor. Let's try determine the correction factor for the first sample in the table. First, what you need to do is to refer to bulk volume in column F. You can refer to your Marshall form. So the first value for bulk volume in column F is 523.7. By having this value, you can refer to the small table where this value is between 523 and 535, and the correction factor can be selected at 0.96. The same thing goes for the next sample where the value of the bulk volume is 520.3, and when we refer to the small table, the value of the correction factor will be 1. Okay, the value of the correction factors need to be determined for all the compacted samples. Okay, next we have a look on column P, Q, and R. As mentioned earlier, P is the value of stability and R is the value of flow. For column Q, the value of stability is corrected by multiplying the value of stability obtained from the test with the correction factor. Then, by using the average value of the stability and flow, we can calculate the stiffness value as shown in column S. That's the final parameters in the Marshall form. So next, what you need to do is to fill in and calculate for all the parameters of the trial bitumen content. So how the final Marshall form will look like after all the calculation has been completed. This slide shows the completed calculation of the Marshall form. As referred to the steps earlier, a few graphs need to be plotted based on the results obtained from the Marshall form. The parameters that need to be plotted are column G, the bulk specific gravity value, and then column M, VFB, column N, VTM, column Q, stability after correction, column R for the flow, and finally column S for the stiffness value. And this value will be plotted versus the trial bitumen content. Bear in mind, only the average value will be considered for the plots. Okay, let's have a look on the graph. As you can see from the slide, these are the plots of density, stability, VTM, VFB, and then in the slide we have flow and stiffness. So in order to select the optimum bitumen content, we need to take the average of 5 bitumen contents selected from the graph. Detailed selection of the bitumen contents can be found in your notes. Here in these slides, I have listed a few criteria for the selection of the bitumen content. The first one refers to the peak of curve taken from the bulk specific gravity graph. Okay, let's have a look on the first criteria based on the peak specific gravity, or we can say the maximum, the selection of the bitumen content at maximum density or specific gravity. Okay, let's say from the graph, we assign the bitumen content at maximum density is A, or in this example, the value is 5%. Okay, take note of that. And then we go to the second criteria is peak of curve taken from the stability plots. Okay, if we look at the graph in the slide, the peak or the maximum stability, the bitumen content is assigned as B, with the value here is 5%. And then the next criteria is on VTM. So in here, the criteria for VTM is based on the mid-spec, which is 4% for wearing cost and 5% for binder cost. Why? Because if you refer to table 2.3, VTM, the range acceptable based on the specification is at 3 to 5%. So the mid-spec will be 3 plus 5 divided by 2, and then we've got 4%. And then for binder cost, the limit is between 3 to 7%. So that's why the mid-spec is 5%. Let's assume the data plotted in this slide is for wearing cost. So now the determination of bitumen content at mid-spec of VTM is at 4%. So C assigned here for the bitumen content is 5%. Next, we have the criteria for VFB. So here VFB equals to 75% for wearing cost and 70% for binder cost. So looking at the graph plotted here, again we assume as for wearing cost, the value of bitumen content assigned as D at mid-spec of 75% is 4.9%. And finally, the flow criteria is equal to 3 mm, which is the average of 2 to 4 mm. So looking at the flow graph, now the value of bitumen content assigned as E is 3.8 at the mid-spec of 3 mm. So based on the 5 criteria just now, we have selected the bitumen contents of each criteria. Then, now we can calculate the value of optimum bitumen content by taking the average of these values. So based on the calculation, the value of OBC obtained from this example is 4.7%. So what we need to do next is to check the parameters whether this OBC value of 4.7% comply or not with the standard specification. Okay, again, we have to refer to the plotted graph. Using the OBC value of 4.7 obtained from this example, let's determine the density value and then stability, VTM, VFB, flow value, and also the stiffness value. This table summarizes the parameters obtained from the OBC for stability, flow, stiffness, VTM, and VFB. So using this value, we have to compare with the specification. In this case, we have to compare with the wearing cost specification. By comparing the value obtained from the plots at OBC 4.7, all the criteria are seems to comply with the standards and can be used for the production in plants. Bear in mind, if the designs fail to comply with the specification, then the job standard mix need to be repeated. Okay, that's all for now. I hope you can understand about the Marshall mix design. Thank you very much for listening. See you in the next video. Assalamualaikum.